If you've ever looked at a job listing for a software developer, you've probably seen 3 letters listed as a mandatory requirement: OOP. In the early days of programming, software was written as a long, continuous list of instructions. It worked for simple tasks, but as programs grew, that code became a tangled mess. Pull on just one wire, and you could break the entire system. Object-oriented programming, or OOP, changed how we organize our code. Instead of a massive list of commands, developers started grouping data and instructions into independent, self-contained units that mimic items in the real world. This simulation tracks independent items: a piano, an oven, an aquarium, each strictly responsible for its own behavior. This allows the game to manage hundreds of moving parts at once without crashing. By breaking the software down into these smaller, self-managing pieces, developers can build complex systems without the software collapsing under its own weight. To see how we actually build these independent pieces, let's look at how a factory manufactures a smartphone. Every phone starts as a blueprint, a class. It maps out properties like brand and storage, and actions like calling. But you can't make a call with paper. The class just defines rules. To make a call, we build a physical copy called an object. Because the object is separate from the blueprint, you can use that exact same template to create unique phones. One object might be assigned the data for a red iPhone, while the next object becomes a blue Galaxy. Separating the instructions from the physical item means developers can scale up production to any size. They write the core design once and then generate as many independent objects as they need. Once you have all these objects running in your software, you need rules to govern how they interact. These rules are known as the 4 pillars of OOP. The first pillar is encapsulation. This is the practice of keeping an object's internal data shielded. You can see this principle in this early automated teller machine. The customer is physically isolated from the cash and the bank's internal ledger. If she wants to withdraw money or check her balance, she can't just reach inside and alter the numbers herself. She has to use the public keypad to request a transaction. Encapsulation does the same thing for software. It creates a protective firewall around an object's sensitive data, ensuring that other parts of the program can't accidentally alter or corrupt it. The second pillar is abstraction, which focuses on hiding unnecessary back-end complexity from the user. Think about what it takes to drive a car. You don't need a degree in mechanical engineering to get to the grocery store. The moving pistons and exhaust systems are hidden under the hood. They fade away, leaving you with a simple steering wheel and a gas pedal. Abstraction ensures that software objects only expose the few simple controls another program actually needs, keeping the rest of the mechanics out of sight. The third pillar is inheritance. This lets developers reuse existing code to avoid performing redundant work. In a racing game, a main category called vehicle establishes shared traits like wheels and an engine. To program a sports car or truck, you create specialized versions from that main blueprint, adding only their unique features. By passing down traits through a hierarchy, developers reduce the amount of repetitive work required to build out a complex system. The fourth and final pillar is polymorphism. The word translates to many forms, and it means a single command can trigger different behaviors. Imagine 3 different digital objects: a simulated dog, a simulated cat, and a simulated cow. If the system sends all 3 of them the exact same command to speak, the dog barks, the cat meows, and the cow moos. They understand the shared instruction, but execute it in a way aligning with their unique identity. Polymorphism lets developers write flexible programs where they can issue broad, unified commands without having to micromanage exactly how every single object responds. If you're sitting in a job interview and the hiring manager asks you to explain object-oriented programming, you now have the tools to answer clearly. Let's do a quick recap. If they ask what a class is, you know it's the blueprint. When they ask about an object, that's the actual usable version manufactured directly from that blueprint. And the rules that keep these objects functioning safely, those are the 4 pillars: encapsulation, abstraction, inheritance, and polymorphism. Object-oriented programming solves the tangle of early coding by providing structured, modular pieces. It allows development teams to reuse code, secure their data, and build applications that can scale to any size.